Hi, welcome to my video. Here I'm going to explain the topic of my research, which is the expressive power of homomorphism counts. I'm going to start off with a quick definition of graph. A graph is a pair G of two things where VG is the vertex set, which is a finite set, and EG is the edge set of G. So note that for two vertices that are distinct, U and V, they form an edge even only if VU forms an edge in G. And here is an example of two graphs G and H, where, for example, in G we have V1 that is connected to V2, they form an edge. Next up, homomorphism. Given two graphs G and H, a homomorphism from G to H is a function H that maps all the vertices of G to the vertices of H, such that for all distinct vertices UV in G, if UV forms an edge in G, then their images under H also form an edge in H. So let me illustrate the definition here using the two graphs G and H from the previous slide. We have a homomorphism that maps V1 to V5 and V2 to V3, and it is easy to check that this mapping is a homomorphism because V1 and V2, they are distinct and they form an edge, and their images, which is V5 and V3, is also an edge in H. A similar notion to homomorphism is the more commonly known isomorphism. So, given two graphs G and H, an isomorphism from G to H is a bijection pi from the vertices of G to the vertices of H, such that for all distinct vertices UV in G, the pair UV is an edge in G even only if their images is an edge in H. And in fact, isomorphism is an equivalence relation over all graphs. And by the way, isomorphic literally means structurally identical. And here is an example of two graphs that are isomorphic. And in fact, there is an isomorphism that witnesses the fact that G and H, they are isomorphic by this mapping from V1 to V4, V2 to V6, and V3 to V5. Homomorphism counts, specifically the number of homomorphisms from F to G, is denoted in this way, and homomorphism counts play the central role of my research. Let me illustrate the definition here. So, for example, we have three graphs here, F, G, and H. By simple counting, we can find that there are actually four homomorphisms from F to G. Like, for example, V1 can go to V3, while V2 can go to V4 or V5. And by simple counting, you will find that there are four homomorphisms from F to G. And likewise, there are four homomorphisms from F to H. In fact, it turns out that for arbitrary graphs F, we have that the number of homomorphisms from F to G is the same as the number of homomorphisms from F to H. And it turns out that this condition, which is highlighted here, entails that G and H, they are isomorphic. And this is known as Lova's theorem. And let's look at homomorphism counts from the other direction. You will find that by simple counting again, that there are two homomorphisms from G to F, and likewise, there are two homomorphisms from H to F. And you will also find that for arbitrary graphs F, the number of homomorphisms from G to F is the same of the number of homomorphisms from H to F. And it turns out that the highlighted condition is sufficient to conclude that G and H, they are isomorphic. And this is known as Choudhury-Vardy theorem. Therefore, from the two theorems that we have seen earlier, they are actually characterization of graph isomorphism. In other words, isomorphism coincides with the equivalence in terms of this form, that is, homomorphism counts from all graphs to a given graph here. And likewise, from the characterization of Choudhury-Vardy theorem, we have that isomorphism coincides with equivalence in terms of homomorphism counts in this form. So if we consider not all the graphs, but rather just certain graphs, then the condition given here, the two conditions given here, they both give rise to an equivalence relation that are coarser than isomorphism. And therefore, it is natural to ask the question, like, for what equivalence relation is it true that this given equivalence relation can be captured by equivalence in terms of homomorphism counts in this form, where F is drawn from certain class of graphs? And the dual question is like this, that for what equivalence relation is it true that this equivalence relation that is given is the same as equivalence relation that arises from having the same number of homomorphisms to a certain class of graphs? If we look at the two characterizations of isomorphism from a different perspective, we have this statement. For a given graph H, the class of all graphs G that are isomorphic to H is the same as the class of all graphs such that this condition, it is satisfied. And likewise, from the Choudhury-Vardy theorem, this class of all graphs G that are isomorphic to H is the same as the class of all graphs G such that the condition holds. And this gives rise to a natural question like this. For what class C is it true that the membership of graphs in this class C is totally determined by homomorphism counts in this form? And there's a dual question. For what class C is it true that the membership of all graphs in the class C can be totally determined by homomorphism counts of this form? And so my research is concerned about the questions of the four questions stated here. Thank you for listening.